trig identities numerically and graphically. By trig expressions in one primary or reciprocal trig ratio. A trigonomic identity is a trigonomic equation that is true for all permissible values of the variable in the expressions on both sides of the equation. So when we work with an identity, what we're trying to prove is we're trying to prove that the left side of the equation is actually equivalent to the right side of the equation. So we're not trying to solve the equation, we're proving an identity that this expression is equal to this expression. So thinking back to like our junior high days and solving a equation, if I were to solve this equation, collect my like terms, move x's to one side, numbers to the other, and then solve for x, I get an x value of 9. So because of our algebra skills are fairly strong now, we don't ever really go back and check to see if this answer is correct. We feel fairly confident that it is. But a numerical identity would be to substitute this value back into the expression and prove that the left side of your equation is equal to the right side. So the identity part is like checking your answer. So I'm going to substitute 9 back in for my x value. And I'm going to simplify the left side of my equation. And then I'm going to simplify the right side of my equation. And if my left side equates to my right side, then I've proven that the identity is correct. I've proven that my solution is correct. Okay, so that's the idea with this entire chapter, chapter 6. We're going to be basically simplifying identities, proving them both numerically, graphically, and algebraically. So we're going to be introducing lots of specific trig identities today, tomorrow, and the next day. So when we consider identities, we always got to consider things like non-permissible values. For what values is the identity not valid or not true, right? So a trigonomic identity is an equation that is true for only the permissible values, not the non-permissible values. So when we think about the tangent function, because we've learned that tangent can be written as sine of theta over cosine as a fraction or as a division statement, we also know that as soon as we start to divide values, this expression in our denominator cannot equate to 0, because if I take sine of theta divided by 0, I'm going to get an undefined value. So when we talk about our non-permissible values are going to occur where cos of theta cannot equal 0. So it's going to occur, thinking about our unit circle, when is cos of theta equal to 0, right? Well, that would occur at pi over 2 and 3 pi over 2. But I want to write this as a general expression for all possible rotations around my unit circle. So these two expressions, or these two angles, relate to each other in terms of a pi. So rather than writing both of these values within one rotation, I want to talk about all the non-permissible values, which would just be pi over 2 plus n, where n belongs to the integers. And then similarly, if I wanted to talk about the non-permissible values for secant of theta, well, secant of theta is technically the reciprocal of cos of theta. So this could be rewritten as 1 over cos of theta. Again, I can't divide by 0, so my non-permissible values are going to occur where cos of theta cannot equal 0. So my non-permissible value would be theta cannot equal pi over 2 again, plus n pi. Sorry, and this should be theta cannot equal these values. Okay, so that's what we're looking for permissible values. We're looking at the expression, thinking about can it be written in fraction form, and what is this denominator in the fraction form, knowing that this cannot equal 0. So those would be our non-permissible values. All right, so now we're going to introduce our reciprocal identity. Kind of already talked about these. Cosecant is 1 over sine, secant is 1 over cos, cotangent is 1 over tan. Quotient identities, we've already seen these. Tangent of theta we know is sine divided by cos. Cotangent is cos divided by sine. And then we're going to introduce our Pythagorean identities. All of these are on your formula sheets. So is this first Pythagorean identity, cos squared x plus sine squared x. This comes directly from our unit circle. So if we think about our unit circle, right, this represents x, this is y, and we know on our unit circle the radius 1. And so using Pythagoras, right, these three sides relate to each other using x squared plus y squared equals 1 squared. Well, technically we know x represents cos of theta on our unit circle, so cos squared of theta. Y represents our sine squared of theta, and then 1 squared is equal to 1. So this identity comes from. What I want you to recognize is that we can isolate sine in this Pythagoras identity when we want to in order to use it and replace values in our identities. So if this is not on your formula sheet, but just recognize if I know my Pythagoras identity, I can rearrange this for cos of theta, cos squared theta, which would be 1 minus sine squared theta, and I can rearrange it, which would be 1 minus cos squared theta. A couple other Pythagoras identities to keep in mind is 1 plus tangent squared of theta is equivalent to secant squared theta, and cotangent squared theta plus 1 is equal to cosecant squared theta. All right, and then use these identities to prove more complex identities. Okay, so in our first example here, it says given the identity cosecant of theta should be equivalent to cotangent of theta divided by cos of theta. So when we think about this expression or this identity, first thing we want to do is determine non-permissible values. So when we think about non-permissible values, we have to consider pretty much all of these values. Okay? We wouldn't have to consider the numerator here if it was just sine or cos, but because it is cotangent, and cotangent is equivalent to cos over sine, we have to consider that as a non-permissible value. So we have to consider this values for non-permissible value, which is 1 over sine. And so our non-permissible values for this would be when sine of theta cannot equal 0, which would occur at 0. And because our domain down here is 90 degrees, we're going to work in degrees. So 0, 180, and 360. Now I'm going to list my non-permissible values for cotangent. Well, cotangent is cos over sine. So again, we have this sine in my denominator. So again, we're going to find the values when sine of theta does not equal 0. Same as what we got here. So we don't have to write it again. And then the last one is this, we have cotangent over cos. So we want to look for when cos of theta cannot equal 0, which would have 90 degrees and 270. So technically, if we think about our unit circle, we're going from 0, all of our non-permissible values would be 0 to 90, 180, 270, 360. So technically, all of these relate to each other within a 90-degree angle. So my non-permissible values for this entire identity would be theta cannot equal every 90-degree angle times n, where n would be belong to our integers. Even though this is 0, 180, 360, this is 90 and 270, they all are related to each other within a 90-degree angle, so we don't have to list them all. We just need to list 90. All right, so that was the first bullet. The second bullet, it says numerically verify that 45 degrees and pi over 6 are solutions for the equation. So to numerically verify, this is our check. We want to substitute this value in for our angle, and we want to prove that the left side is equivalent to the right side, and you should always be doing this in exact values. So maybe let's just add that. Okay, so this was our first bullet, so let's do our second bullet here. So I'm going to substitute 45 to 2 my identity, and I'm just simplifying the left side of my equation, and I want to make it equal to the right side. And right now, so cosecant of 45 degrees. So if we had our unit circle, we're looking 45 degrees up. We're talking about cosecant. So cosecant is the reciprocal of sine. So if this is root 2 over 2, the reciprocal of that would be 2 over root 2. And I'm just going to leave it as 2 over root 2 for now. We don't have to, we're not solving an equation. We're just proving that the left side, as long as your answer on the left looks exactly the same as the right, then it's good. You don't have to rationalize or anything like that. Okay, so then we're going to look up cotangent of 45 degrees. So 45 degrees, cotangent would be cos divided by sine. So anything divided by itself would be 1, right? So cotangent is 1 there. So this would be 1 divided by, now we want to look up cos of 45 degrees, which is root 2 over 2. So this would be my first step to simplifying this. So I really don't need to do anything with my left side. I am now going to think about how do I divide fractions. Well, to divide fractions, we want to take the first fraction and multiply it by the reciprocal of our second fraction. So it's technically 1 times 2 over root 2. Multiply this together, and I get 2 over root 2 equals 2 over root 2. I've just proved the identity numerically. Okay, we're going to do the same thing, but we want to prove it for a different angle, which is pi over 6. So we're going to take cosecant should equal cotangent of pi over 6 divided by cos of pi over 6. So again, I'm these up on my unit circle. Cosecant is the reciprocal of sine. Pi over 6, my sine ratio is 1/2, so I'm going to reciprocate that to be 2. So this should be 2. Cotangent, okay, so if you've written your tangent ratios out, I believe, our tangent ratios is normally sine divided by cos, which gives us 1/2 times 2 over root 3. So our tangent ratio here is 1 over root 3. So you can go off this if you remember your tangent ratios, or you could, instead of dividing sine over cos, we could divide cos over sine. It honestly doesn't matter, whichever way you decide to go. So if we went with, assuming I didn't have my tangent value, because it's cotangent, cos divided by sine. So I'm going to go a over 2 divided by a 1/2. And then I'm going to put that over, divide that by cos of pi over 6, which is simply a root 3 over 2. So then I'm going to simplify this fraction up top. Technically, what I end up getting is a root 3 over 2 times the reciprocal of that, which is 2 over 1. That cancels. And this ends up, entire expression up top is just a root 3. So what I have here on the right side of my equation ends up to be a root 3 over 2. So now I'm going to divide these fractions. So I still have 2 over here. I'm going to take a root 3. Technically, this would be over 1. I'm going to multiply that by the reciprocal of my denominator. My root 3's are going to cancel, and I'm simply left with 2. So 2 equals 2. So my identity works out for my 45-degree angle as well as my pi over 6. So as you can see, when you're proving an identity, you are never moving things back and forth from one side of the equation to the other. You should never move things. We are simply working on the left side or the right side and trying to equate those values to equal one another. And then it says, use technology to graphically determine whether the equation could be an identity over the domain of negative 360 to 360. So now I want to graph this on my calculator. And technically, some of the newer calculators are nice because they give different colors. And I'm going to graph my left side, which is cosecant of theta, which would be the reciprocal of sine. And on the left side, cotangent is the reciprocal of tan. So I'm going to put that in brackets. So that's my cosine. And then I want to divide, cotangent. And then I'm going to divide that by cosine. So here's my two equations. So if you do not have two different colors on your calculator, if you move your cursor over in Y2 to the very left, and right now it's going to draw a thin line. If you hit enter one time, because technically if this is an identity, the left side of your graph should be the exact same graph as the right side. So you're not going to see the two different graphs being drawn and Y2 value. Okay, so when I graph this, before I do that, let's think about my windows. My windows need to be negative 360 to 360. My domain, a safe zone is always like negative 5 to 5 for your Y value. Because my domain is in degrees, you need to make sure your mode is in degree, and then we're going to graph this. So here's my first graph. So we've got asymptotes going on, non-permissible values, right, every 90 degrees. And then look, my second graph is being drawn, and you can see because it's a thicker line, it's clearly being drawn over top of the original graph. All right, so looks good. So what can we say about this? We can say that the left and right side of the equation create identical graphs. This is a trig identity. So the identity is true. Okay? So proved it numerically, proved it graphically. Okay? All right, so moving on to question number 3. It says, given the expression, determine the non-permissible values. Then it says simplify the expression. So we're just simplifying the expression. It's not an identity because we don't have an equal sign here separating it. It's just an expression that we want to simplify, and usually want to simplify into a single trig ratio. So let's first talk about our non-permissible values. So we have a tan of x. I don't have to worry about my cos of x because that's here, and it's not reciprocated. I have to worry about secant of x, which is 1 over cos, and then I have to worry about cotangent. So first, let's think about our tangent. This is sine over cos. So we got to think about when cos of x does not equal 0. And that would be at pi over 2. and 3 pi over 2. And then we're going to worry about secant. Well, secant is technically the reciprocal of cos. And so the same non-permissible value as this, right? When is cos of x not equal 0. And then we're going to worry about our cotangent, which is cos over sine. When is sine of x not equal to 0? Would be at 0, pi, and 2 pi. So what would our non-permissible values be? Our non-permissible values would be x cannot equal all of these values. Well, again, all of these values are related to each other by a half a pi. So it'd be basically just half a pi n, where n belongs to the integer. Okay. So that's the first part. Now we're asked to simplify the expression. So to simplify the expression into a single trig ratio, we want to use these reciprocal and quotient identities that are on our, so you're going to like replace tangent of x with sine over cos. Your secant potentially with 1 over cos. And cotangent we can replace with cos over sine. So this is what we want to do. So tangent of x is sine, I'm going to replace, let's just go back up here, we'll separate this. We're going to replace tangent of x with sine of x. So it's really important that your fraction skills definitely come into play in this chapter. If you don't have any fraction skills, then you're going to struggle. Cotangent is cos over sine. We have like fractions within fractions here. So now we're going to start to look to see, well, can things cancel? Because this is a cross multiplication, cos of x is technically over 1. I could cancel this and this. In my denominator, my cos of x is also canceled. So what I'm left with is sine of x over 1 over sine of x. So now I'm dividing these fractions. I'm going to multiply by the reciprocal. So from here, this would become sine of x times sine of x over 1. Sine of x times sine of x is a sine squared x. So all of this expression simplifies to just sine squared x. Okay, so this is kind of the start of identities, where we're using other identities to simplify an expression. Okay, so question 4, it says, use quotient identities to express the Pythagorean identity cos squared x plus sine squared x equals 1 as the equivalent identity to cotangent squared theta minus cosecant squared theta equals -1. All right, so what we're going to start with is we want to basically prove that these two are equivalent. I really can't do anything with cos or sine, so instead of working with this identity, we're going to work with this identity. I can change cotangent to cos, and if it's cotangent squared theta, then this would just be cos squared theta over sine squared theta. If it's a cube, then it would be a cos cubed over a sine cubed. Okay, I can replace cosecant with 1 minus sine squared theta. What we are trying to do is we're trying to get to a point where this is going to equate to this. Okay, so from here, right, we don't like working with fractions. Here we have absolutely no fractions. So we are going to multiply this entire equation by our lowest common denominator, which would be sine squared theta. So I'm going to take a sine squared theta and I'm going to multiply it by this fraction. I am going to multiply sine squared theta by this fraction. I also do this on the far side of my equation, so I'm going to multiply sine squared theta times a negative 1. All right, so when we do that, so as long as you're multiplying everything by the same value, you're allowed to do that. So look here, these cancel, so I'm left with cos squared theta minus 1 equals a negative sine squared theta. Okay, so technically this gives me my Pythagorean identity. If I move this to this side and this to this side, we have cos squared theta plus sine squared theta is equal to 1. So it takes all of these steps to prove that these identities are actually equivalent. Okay? Okay, and then the last one, it says try to simplify the following: 1 minus sine squared theta over cotangent squared theta times secant over tan. All right, so thinking about, we start to recognize this expression and 1 minus cos squared theta. This comes from our Pythagoreous identity, where I can isolate for either one of these values. So if I moved sine squared theta to this side of to cos squared theta, so a 1 minus sine squared theta is equal to cos. So I'm going to replace this with just a cos squared theta. I am going to replace cotangent with cos over sine, and then I'm going to multiply this by secant is 1 over cos, and then I want to divide that by sine over cos. Okay, so I am going to, rather than multiplying these, I'm going to simplify this fraction and simplify this fraction before I actually multiply them together. So how do I divide fractions? I take the numerator and I multiply it by the reciprocal of the denominator. So that's this set. And then that is being multiplied by, same thing, I'm going to take the numerator and multiply it by the reciprocal of the denominator. And then I'm going to start to look to cancel. So here my cos squareds cancel, my cos cancels here, and now I can multiply these. So